So hello, it is a pleasure to greet you again at this sixth edition of the One World YoungStatS series. YoungStatS is a project taking place in the framework of Young Statisticians Europe of the Stats Association. It is supported by Bernoulli Society for Mathematical Statistics and Probability and Institute of Mathematical Statistics, IMS. The topic of today's webinar and basically is advancements in symbolic data analysis. With the development of digital systems, very large data sets can become routine. However, standard statistical approaches do not get the power or flexibility to analyze this efficiently. So symbolic data analysis, as the A is its abbreviation, provides a framework allowing for the representation of data with intrinsic variability, where the observed values are not just single real values or categories, but finite sets, intervals, or distributions over a given domain. Methods for the multivariate analysis of such symbolic data have been developed following different approaches and using distinct criteria which take this data variability into account. So we have the pleasure of greeting 4 selected young leading researchers in the area today to present their contributions. We have with us Professor Yuying of Chinese Academy of Sciences, Beijing, China, who will present on model averaging for interval valued data. We have Dr. Boris Beranger of University of New South Wales in Australia on the topic of using symbolic data to understand underlying data behavior. Bruno Pimentel of Universidade de Alagoas, Brazil, on cohort mapwise regression applied to interval data, and Sónia of Polytechnic Institute of Viana do Castelo, Portugal, to present on discriminant analysis of distributional data. The discussant for today's webinar will be Professor Paula Brito, who is Associate Professor in Statistics and Data Analysis at the Faculty of Economics of the University of Porto, and also member of the Laboratory in Artificial Intelligence and Decision Board of this same university. She is an expert in symbolic and multivariate data analysis. So I shortly additionally mentioned when we are with Paula, but she will mention this herself. There is a large conference in 2022 from the IFCS, International Federation of the Classification Societies. So also possibilities to discuss these topics further also in next year. So without further ado, I will give the floor to Yuying to start with her presentation. I apologize if I didn't introduce somebody of the speakers enough, and I suggest he or she does this, him or herself. So please, Yuying, the floor is yours.
Thank you, Andrew. I'll share my screen.
Great.
Can you see this screen?
Yes.
Okay. Let me switch to the tablet, and also I'll turn off the camera to make this data flow smooth. So
can you make your slides little bigger?
So I have to. Okay, sure, that's fine.
Yeah. That's better now. Yes.
Is it better? Okay.
Yes.
Yeah. So good afternoon in Beijing time, everyone. I'm Yuying from Chinese Academy of Sciences. First, I'd like to thank Professor Paula Brito for this and Andrew for this kindly invitation. And it's my pleasure to share one of my work here. This is also a joint work with Yuying from Chinese Academy of Sciences, Alan Wan from City University of Hong Kong, and Shouyang Wang from Chinese Academy of Sciences. This paper is entitled as Model Averaging for Interval Value Data. And this is outline on my talk. First, I'd like to introduce some basic backgrounds and motivations to explain why we consider model averaging or linear combination for interval data. Well, the traditional time series has been concerning modeling point value time series data, but the technology progress encouraged the popularity of modeling new types of data. So interval data, or more generally, symbolic data, are of increasingly available in practice. So if one just uses this conventional point, one may reach the informational limits, especially for time series analysis. An interval observation in time period usually contains more information than point data in the same time period. So here are some examples here in practice for interval time series. The first one is one of the examples, the temperature process. So we can actually collect data like daily intervals for temperature. And so we have the interval value time series and the two boundaries. And here, two boundaries. It is a minimum and a maximum of daily temperature. So we have this interval value time series. And in finance, we usually encounter interval time series like stock prices in trading periods. For example, the daily price interval for stock. So the interest here is the spread of this interval. So the spread of this interval, it is a measure of volatility. It is also called Parkinson range. And so it is important for econometrics. Besides, there are other types of examples for intervals. They are like self-formed interval. So examples are big as a spread here. At each time point t, we have this big ask price for asset price. So this interval, we can interpret as a set of enclosed or the possible potential trading processes for this asset. And the spread of this interval here is what we call big ask spread. So they are all like interesting things for economics and financial data. With the available data information, we have faced a large number of candidate models for interval value data. One method is model selection, which aims at choosing an optimal model for making a prediction. And many popular point-based model selection criteria can be used for interval value data, like BIC and AIC. However, many studies found that the procedures to select the best model from a set is unstable. In the machine learning literature, Bruno is a person who proposed random forest. Based on his consulting empirical experience, he found out that given the data, usually the training data or test data or evaluation data, they are doing out-of-sample forecast. Assuming there is a high dimensional covariance, there are many variables. When we change the training data set with adding or deleting a few observations, the best model is going to change. So here is one of examples. And if we give in this data, this is the training data. The model 1 is the best model. It has X3, X8, X12, and X17 and X27. However, when we add two observations in this training data set, the best model is going to model 2. This is the best model. But model 1 is totally different from model 2 is totally different from model 1. And this phenomenon is called model uncertainty. Adding or deleting a few observations, the best model is going to dramatically changing. So how to deal with model uncertainty? An approach to reducing model uncertainty is to use a linear combination, also called model averaging. The idea goes back to Beranger in 1969 in forecasting the number of airline passengers. And he found that the combined forecast outperformed other single forecasts. Model averaging can be roughly divided into two groups. One is Bayesian model averaging. The other is frequentist model averaging, which aims at selecting the optimal weighting from candidate models. Since Hansen, in his paper published in Econometrica in 2007, he proposed model averaging and found the asymptotic optimality of the selected weight. Then frequentist model averaging has drawn increasing attention during the last decade. For example, Andrew Lee, they proposed cross validation for high dimensional data. John with co-authors proposed KL laws for non-normal data. So this year, we have a paper published in Journal of Econometrics. We propose time-varying jackknife criterion for time series data with structural changes. However, all these works are developed for traditional point value data. This paper is the first one to propose model averaging framework for new types of data, like interval data. We adopt two model averaging criterion for midpoints and ranges, and both of them are based on unbiased estimators of the expected squared errors. We prove that asymptotic optimality for the midpoints and ranges weights, and a method is further developed for correcting the range forecast. Simulation studies and empirical applications highlight the merits of the proposed method. So this is our data generating process. First, what is an interval? A regular interval is defined as a set of all the real numbers like this way. So A here is a lower bound and B here is an upper bound. So we'll assume there is a natural order in this interval. That is, the lower bound is smaller than the right bound in the upper bound. So the range here is positive. To guarantee this natural order, we consider a model for midpoints and log ranges of interval data. This setting has been widely used in the existing literature, such as in Brito and Silva's paper. So at here, we consider the VR process for this midpoint and log range. And this is interval data. It is determined by midpoint and range respectively. And then at here, we consider the data for midpoint and the log range. So we use tilde here. Tilde here means log. So this notation is for the log range. And mu t here is the conditional mean. It is conditional mean for the midpoint. This is conditional mean for the log range. Note that we model the log range here, but our interest still the original range. Then this is candidate models. And we consider S is the S model, and S is from 1 to capital S. And we found that in this model, we can assume all candidate models are nested or non-nested. And we can assume all candidate models are misspecified. Then we can get this metric form to get the candidate models. And we use S here. It means the S candidate model. And from this model, we can get the model for midpoint and get the model for the range, for the log range. Then we follow Liao's paper in GOE, and we use the least square estimator to get this estimator for the parameter estimation in candidate models. And then we can get the estimator for midpoint and the estimator for the log range. Then we can get, this is the estimator of the conditional mean in the SS candidate model. And this is the estimator of the conditional mean for log range in the SS candidate model. And this is the estimator of the conditional mean for the range. Then we do model averaging here. And this is the weighting for midpoint, and this is the weighting for range. And we say that M here, it means for midpoint, and R here, it for range, not for log range. And we assume both weighting belong to this set. All weighting are non-negative and summed up to 1. Then we can get the model averaging estimator for the midpoint, and we can get the model averaging estimator for the range. And from here, we see that the weight for midpoint and the range are different. So this is one contribution of our paper. Then we discuss about weight choice criterion. So this is a weight choice criterion for this midpoint. And this is squared error loss. This is a midpoint, conditional mean for midpoint. We know that this loss is infeasible because this conditional mean is unknown. So at here, we want to propose a feasible criterion. And then we follow Hansen's idea to use this Mellows criterion here. We use mu hat minus y to replace mu hat minus mu. And then we also plus this penalty term. By minimizing this criterion, we can get this weight. Then we can get model averaging estimator for the conditional mean. Similarly, we consider the squared error loss for the range. Note that this loss is for range, not for log range. So we have exponential here. But as we know, this term is conditional mean. It is unknown as well. So this loss is infeasible. We have to propose a feasible criterion. We propose this criterion, it is feasible. Why we use this criterion? Because when we assume YT is IID random sample, we can find that this criterion is the expectation of the infeasible loss plus a constant. So by minimizing this criterion, this feasible criterion, we can get the weight for the range. Then we can get the averaging estimator for the range here. Next is an important theory in our paper. This is called the so-called asymptotic optimality. It means that if this weight estimator is selected from minimizing the feasible Mellows criterion, and we found that this weight could achieve the minimum value of this infeasible loss. So this loss is infeasible, but if we use the selected weight from the feasible criterion, we can get this infeasible loss as minimum. And we also can get a similar result for the range. No matter the candidate models are correctly specified or misspecified, this optimality is true. Then we propose some conditions to prove this asymptotic optimality. And as we know, the panel term, this is a variance in the panel term. So it is this parameter is unknown. This variance is unknown, so we can use its estimator. We found that if we use its estimator in panel term, and we can get a feasible Mellows criterion. By minimizing this criterion, we can get the weight for midpoint is asymptotic optimality. Similarly, we can get this asymptotic optimality for the range. And as we know, this is unknown as well. If we use this estimator, we can get asymptotic optimality for range. After that, we do a correction for the range estimator. Why? Because as we know, the estimator of the log range is unbiased. However, we consider about the original range. So its exponential form is biased for ranges. It means that we miss this term. And then we times this term in our model averaging estimator. And then we can get this mean square forecast error after correction. And we found that this mean square forecast error's expectation is asymptotically equal to the loss before correction times this term plus a constant. So it means that if our weight are selected from the feasible weight choice before correction, the asymptotic optimality is also valid. Then there's a data generating process here. And we assume the midpoint and log ranges have different coefficients like rho here. And we consider for data generating process. The first one is bivariate regression. It likes that the number of covariants is infinite. And we consider the DDP2. It is like a VRMA process. Like a VRMA process. And this is like a VRMA process with infinite covariate. And this is like just a simple MA process. And for data journey process 1, 2, 3, we assume the number of candidate models is 10 and all candidate models are nested. For DDP4, we consider non-nested candidate models and the number is 3. They are different settings. We consider 3 forecast criteria. This is the mean square forecast error for midpoint. This is the mean square forecast error for range. And this is the mean distance error for midpoint and range together. And this is result. This is mean square forecast error for midpoint. And this is the summary result. And OPT is our method. And this is smooth AIC, smooth BIC, AIC model selection, BIC model selection, and the simple averaging. It is the full model. And we found that in 34 cases, our method yields the best forecast in 50 cases and yields the second forecast in 14 cases. So in most cases, our method performs much better. This is mean square forecast error for ranges. And we see that in most cases, our method performs much better than other methods. And this is the criterion for interval for midpoint and range together. And we also found that in over 70% of cases, our method performs much better than others. This is an empirical application. We do interval valued crude oil pricing forecasting. The range is from 2016 to 2019, and we use log prices. Both of them, all of them are daily data. And after ADF test, we model the stationary interval value return like here. And we consider 8 candidate models, including 5 lagged variables and 3 exogenous variables. And we also consider 2 benchmark models. One is center range method proposed in 2008, and the other is constrained center range method. It means that to guarantee the range is positive, they assume the coefficient is non-negative. This is our result here. OPT is our method. There are different auto-sample forecast period, and we found that our method perform much better than others. Then we use Hertz paper to use this trading strategy in our method and evaluate annualized return to evaluate whether our method perform much better. So this result here, OPT is our method. We consider 2 different evaluation periods. One is here, the other is here. And this is the criterion. The larger the result, the better the forecast. And we see that our method still forecast much better. So let's conclude this talk. Yeah, this paper develops a new model averaging framework for interval value data. It is shown that the proposed method are asymptotically optimal in the sense of achieving the lowest mean square errors for midpoint and ranges respectively. And the simulation and empirical application highlights the merits of our method. This framework can be extended to non-stationary interval time series and more general symbolic data, such as histogram data. That's all, thank you.
Thank you, thanks a lot. Clap, I would say. Great, so is there any special question? Short. maybe I will just put one short question. Is this method generalizable also to, I would say, cross-sectional interval data? I think this is a time series model averaging estimator, right? And
yeah.
What would the estimator look like for distributional histogram data, like you mentioned at the end? What would you think?
Oh,
thanks.
Yeah, thank you. This is a very good question. Yeah, because for this interval data, we just consider 2 points, and interval data can be determined by its lower bound and upper bound, or by its midpoint or ranges. So if we extend this framework to histogram data, we maybe consider more data, more point value data, which determines the histogram data. Yeah, so this framework may be more complicated. It's just because this paper is just a simple idea. We also can extend it to many places, such as non-stationary time series. Anyway, yeah.
Great. Many thanks. Okay, in the interest of time, we move forward, and I give the floor now also to Bruno Pimentel, please. Thanks again.
So, good morning, everyone. Can you see the presentation?
Yes. Maybe if you enlarge them to the full screen. Okay. Yes, great.
So, first of all, I would like to thank the invitation to present this work here today. And this work the title is Cohane Map-Wise Regression Applied to Interval Data. It's a collaboration with Leandro, Professor Leandro, Telmo, and Renata Souza from Brazil. So this is a summary. The motivation why I studied the proposed method, which approach we use to propose the method in this work. Experimental evaluation, so you present synthetic and real data sets to evaluate the proposed method compared against the method from literature and some results. And finally, a conclusion about this work. So what's the motivation behind the proposed method? So in order to better understand the method proposed, it's important to understand what is cluster-wise regression, here abbreviated as CWR. So cluster-wise regression combines two main approaches, clustering and regression. In clustering, the goal is to allocate the objects from data set that minimize the distance between a cluster, a prototype of a cluster. In regression, you fit a model that try to understand the relationship between the dependent variable and independent variable. So this is a typical figure about cluster-wise regression. So the difference here, when compare the traditional cluster approach, is that instead of you have a center, a point to represent the center of each cluster, you have now model regression, where the goal is to allocate an object from data set that minimize the error to regression. So there are many applications to cluster-wise regression due to this importance to model data sets. So you can find applications in several domains, such as prediction of incomings, predictions of rainfall, estimation of crash frequencies, and so on. Another approach that is important to understand the proposed methods is called sum-wise regression, here abbreviated as SWR. So this approach is more flexible than the traditional CWR because sum-wise regression has two main structures. At the high level, you can find the Cohon self-organized map, known as SOM. And at low level, you can find the multi-layer perceptron MLP, where each unit from SOM structure is a MLP. So this is a typical picture to represent the SOM. So the main characteristic of this SOM Cohon self-organized map is this map where nodes are distributed in this map. They can be connected. There are many strategies to connect these nodes. In this work, you use fully connected nodes. So, SOM-wise regression, we use MLP to take account the input data set, change the weights to minimize the error, and each node make the prediction of the interval data according to the input vector. So each iteration, the weights can change for each MLP, and each node give a prediction of this input. So there are two main advantages to use SOM-wise regression. The first one is that you don't need know the number of clusters to find a partition from data sets. Another advantage is the result can find non-linear partners. So you can find non-linearly separatable clusters from a data set. So this is the main advantage to use SOM-wise regression that you will use in the proposed method. So based on cluster-wise regression and SOM-wise regression, the focus of this work is to introduce a new SOM-wise regression model, more specifically from the framework of symbolic data analysis. This work will use the representation of interval data to model the data set, the prediction of data set. So what's the mathematical behind the proposed method? So we call interval SOM-wise regression in this work, or ISWR, that combines two main approaches: the Cohon method that you have just seen in previous slides, and parameterized method that can find regression models for interval data. So the goal of ISWR is to estimate Y, it's an interval from given partner of object from dataset I, where each bound of this interval, lower bound and upper bound, can model by this combination of linear combination. So for each node of Cohon map, K, you weight from weight lambda, each model, regression model for a bound of the interval. So there is a prediction for lower bound and prediction from upper bound. So K is the number of nodes in the SOM map. Okay. Epsilon is the error of the regression, the prediction of the response for each bound. Okay. The regression models for interval data here in this work is given by this equation. So beta, alpha, and omega are coefficients from regression. Okay. If for each bound, you consider a bound for the input data. So X, it's the data you want to predict. Okay. You call P, G, a set of nodes, p-dimensional sum nodes that are weighted by a value called the lambda corresponding to on node GK. So the next step of the algorithm is to update the weights. Here in this work you choose radial basis function, RBF, to compute this weight. D is the interval distance between the input data and a node K. So larger this distance, lower is the weight of object I from to node K. Sigma is the normalization factor, where the goal is to stabilize the numerical guarantee. So we compute using, there are many strategies also in the literature to choose this value, but here in this work you compute to select the maximal distance between the object I and node K from all elements from the dataset and all nodes from the coordinate map. So D is an interval distance. You can choose Euclidean, city block, and Mahalanobis. This work you use Euclidean. Okay. After, the next step of the algorithm is to update the nodes. So you choose a node called BMU, the best matching unit, to that is the nearest node according to Euclidean distance. So based on this node, the nearest node to input S, you update the node K. So new, and we update this node K in the next iteration based on the previous iteration and based on this part of equation. So ponder are based in the learning rate, and you update this weight is computed also using the RBF function. So the larger is the distance between this node K and the nearest node, lower is the weight to update this node K. Finally, you also update the learning rate. So based on the J, the objective function of this approach, you choose the learning rate that minimizes the criterion. So in this work, you use a Newton-Raphson method to update the learning rate. So this is the algorithm in pseudo code. So you initially find the interval regressive variables, the data set. You have to choose the number of nodes and the number of iteration of the algorithm. So through each iteration of algorithm, you find the nearest node to input X, S. You update the learning rate, update the nodes, and after update all nodes, you compute the regression coefficients. After the algorithm converge and achieve the maximum number of iterations, you return the nodes and the regression coefficients. So this work was recently published in the knowledge-based systems. Okay. So for experimental evaluation, use two types of data sets. The first one is synthetic data sets, and the second one was real data sets for interval data. Use the relatively squared error, MRSE, where the goal is to minimize this error. Okay. So close this value is the goal is to find the values close to 0, values close to 1. It means that the prediction was similar to the average. Any values larger than 1 means that the prediction was badly modeled. So for synthetic data sets, we constructed 4 data sets containing 3 clusters. Variegated cluster has 50 objects. So for the first data set 1, we have classes without overlap, equal intraclass variance, equal intraclass correlation, homogeneous intraclass. And for the second data set, the main difference is the overlap class. The rest is equal. The third data set, you have also overlapping clusters, different interclass variance, but with different intraclass correlation. And the last data set, we have overlap classes with different intraclass variance, different interclass correlation, and the heterogeneous interclass interval size. So for each data set, we will draw a codon bivariate normal distribution, where each pair Z1, Z2, choose 2 variables, you consider as a seed of a rectangle V1, V2. So you can find this rectangle based on this equation. So this Z is the seed. You define the lower bound, upper bound based on these parameters. For data set 1, 2, and 3, you fix the size of interval. So you choose a priori the size. But for the data set 4, you change the size of interval based on this expression. So seed close to the mean of the normal distribution will have a smaller size of interval. But the seeds far from the average, the mean, have larger interval data. Okay. So this is the parameters of the synthetic data sets for data set 1 and 2 in the scatter plot. And for data set 3 and 4, these parameters in the picture. So this is the main results. You change the number of nodes from 6 to 30. So there is no difference between the results according to the variation of the nodes, but you can note, it's important to highlight that difference between the cluster-wise regression and the proposed approach. So for all data sets, you can find better results for the proposed method. For real data sets, you also choose 4 data sets to evaluate this proposed method. So the first one is mushroom data set, second one AKC, the third one climate, and the last one scientific production. So this is the results. For real data sets, you fix the number of nodes as 6. because you noted that the variation of the nodes in the synthetic data sets don't change the results. So you choose the simpler model that can construct the ISWR model. So for that data set, real data sets, also again, the proposed method can find the best results. So conclusion, this work proposed a new summarized regression for interval data. Proposed method does not need to know the number of clusters because you are using a Kohani map. We still need to set the size of the map. Large number of nodes did not seem to imply better results. And the proposed model significantly outperforms the literature for all data sets considering this work. So thank you for the.
Thanks a lot. Okay, virtual lab, naturally. So any question from the audience? Maybe very briefly, but please also ask questions in the chat. One short question and then probably we continue. Was there any special reason for choosing this self-organized map technique? And could other techniques, say from neural perspective, be also used on interval data similar regressions? Thanks.
The question, why use this approach?
Exactly. Could other neural approaches also be used for such regressions?
Yes, the main motivation about this Kohani map is you don't need to choose the number of clusters. So it's a simpler when you compare with against the MLP, for example. So in the neural network, you have to have a large data set to optimize the weights in the neural network. So you spend more time to. And Kohani map, we have several advantages to simpler is a model that you don't need to choose the number of clusters, for example.
Okay, thanks. Thanks a lot. Again,
Thank you.
Clap for a good presentation. And we continue with Sónia. Sónia Diaz, please. Discriminant analysis for distributional data. Thanks.
It's okay.
We don't see the slides.
Yes.
Currently, the slides are not seen. We do not. I do not see them. I just see the blank.
Okay.
Dark area. Black. Everything is black. Yes. Now I see.
Now, okay.
Yes.
Yes.
Great. Great.
Hi, good morning, good afternoon, good evening for all. I would like to thank Andres and Paula for the invitation to talk in this webinar. My presentation is about discriminant analysis of distributional data. This work is a joint work with Adelaide Freitas from Universidade de Aveiro, Paula Amaral from Universidade Nova de Lisboa, and Paula Brito with from Universidade of Porto. This is the outline of my presentation. First, I will present a biological problem where the data is a numerical distributional data. Afterwards, I will talk about some introductory concepts that are needed to develop the symbolic discriminant method for distributional data. Using this discriminant method, we will be possible to classify the observations in one of the two groups. Using these methods, it will be study the biological problem referred in the first point. And finally, I will present the main conclusions and the future work. So, the biological problem. In this case, the goal of this problem is classify a set of 23 species of bacteria considering the complete genome sequence of each species. The bacteria may be classified as gram-positive or gram-negative. The structural difference in this case is that in gram-positive, the bacteria do not have an outer cell membrane. So the contribution of this work is classified bacterial species according to the frequencies of of each nucleotide in genome or in a given position of the codon. Sorry. We have, in this case, a complete genome sequences of 11 gram-positive and 12 gram-negative bacteria. The genome is a collection of genetic information organized in genes, and this information is processed in sets of 3 nucleotides, the codons. The nucleotides are 4, A, adenine, C, cytosine, G, guanine, and T, thymine. Here you can observe the list of the 23 bacteria considered in this study. We have the bacteria, and in here you can see the information about the classification of each of these bacteria and the number of genes in each bacteria. And you can see that the number of genes is different according to the bacteria. Here it's only to observe the sequence of nucleotides for 2 bacteria, one gram-positive and another gram-negative. So in conclusion, we have in this case, we have species, the first lab unities that we consider here. We have 23 bacterial species. For each species, we have genes. The number of genes is different considering the species. And we have a sequence of nucleotides associated to each gene. So in this case, the first level unities are genes. And in this case, the observations associated to each gene is the frequency of the nucleotides associated with gene and in each bacteria species. For example, here you have, in this case, 30% of nucleotide A, 20% of nucleotide T, 10% of nucleotide G, and 14% of nucleotide C. But in some situations, we are interested not in consider as unity the genes, but the species. And because of this, we consider here and microdata when the unities are the species. In this case, the goal is classify the bacteria as gram-positive or gram-negative. And the variables are for the distributions of the frequencies of the 4 nucleotides in the gene. For example, we have here the first variable, and in this variable is the distribution of the frequencies of nucleotide A in each species. Here, the frequencies of the nucleotide C in each species. In the variable 4 is the frequencies of nucleotide G, and in the variable 4, you have the frequencies of nucleotide T. Another case that we consider in this study with the same goal, the classify the bacteria as gram-positive or gram-negative, is one case when the variables are the distributions of the 4 nucleotides frequencies at the first, second, or third codon position. So in this case, we have 4 variables and we consider 3 studies, 1 study to each position, okay? The questions that we will try to answer in this presentation are which study better allows classify the bacteria as gram-positive or gram-negative? How is the discriminant symbolic function used to calculate the scores? What is the distance used in the classification process of the bacteria in gram-positive or gram-negative? So the theoretical concepts needed to answer to these questions are: develop a concept of linear combination that allows working with distributional data, develop a discriminant method that allows working with distributional data, and use the discriminant function to classify observations in one of 2 groups. So here we work with distributional data, and the observations of the variables that we consider here are distributions or histograms. These histograms may be represented by the usual histogram or may be represented by quantile functions. If the quantile function is the inverse of the cumulative distribution function, and because of this, these functions are functions with domain between 0 and 1. These functions are also no decreasing functions, and if we consider the uniform distribution within each subinterval, the quantile functions are piecewise functions, and each piece is a linear function. Here you can see one example. If we in this case we consider the distribution that represents distribution of the frequencies of nucleotide A in this bacteria. This is the histogram. In this case we consider one histogram when the weights associated to each subinterval is the same. And here you can see the respective quantile function. These values are the centers of each subinterval, and these values are the alpha ranges associated to each subinterval. Here you can see the representation of the histogram, and here the representation of the quantile function, that is a function with domain between 0 and 1, and a no decreasing function. When we work with histograms, we need operate with these elements. When we consider the usual histograms, operate with histograms is not easy. And because of this, another possibility is consider the quantile function. And in this case, the operations are operations between functions. But also in this case, we have some problems. So, for example, if we have one histogram, and this is the symmetric of the blue histogram, here you can observe the quantile function that represents the histogram blue. But if we multiply this quantile function by -1, we obtain this quantile function represented here in red. So this function is not a quantile function. This function is not a no decreasing function. So to represent this histogram, the symmetric of the blue, it is necessary you multiply the quantile function of this histogram by -1 and consider the transformation 1 minus t. So, besides that, in this work, we consider the observations of the histogram valued variables represented by the quantile functions. So another important definition is the distance that we can use when we consider 2 quantile functions. The distance that we use is the Malus distance, where that is defined as we can see here. The square of the Malus distance between 2 distributions is equal to the integrate between 0 and 1 of the square of the difference between the two quantile functions. If we assume the uniform distribution across the subintervals, this definition may be rewrite, as you can see here, and when to each subinterval we have the weight multiplied by the square of the difference between the centers plus on 1/3 the square of the distance between the half ranges. This is for one subinterval after we add for all subintervals. Using the Mallow's distance, it is possible to define the barycentric histogram. That is, this histogram is the solution of this minimization problem. The barycentric histogram is a quantile function where the centers and half ranges of each subinterval are the classical mean of the centers and half ranges of all observations. For example, you can see here this histogram and this. The center and half range for this first subinterval is obtained. Consider the mean of the centers and the mean of the half ranges of the first subintervals of these two histograms, and the same for all subintervals. Another important definition is the definition of linear combination of quantile functions. When we consider quantile function, the linear combination is not defined as in classical statistics. It's not possible to consider that this definition of linear combination when we use quantile function, because when we multiply a quantile function by a negative number, we do not obtain a non-decreasing function. If a non-negative constraint are imposed of parameters, a quantile function is always obtained. However, this solution forces a linear relation between the explicative and the predictive variables. To solve these problems, Brito proposed a new definition for linear combination that use the quantile functions. This definition, the definition proposed is this definition, is one definition when the quantile function of the explicative variable is obtained. Consider the linear combination of the quantile functions that represents the distribution of the histogram of the explicative histogram valid variables and the quantile functions that represents the respective symmetric histograms. So in this case, we have non-negative constraints in parameters, but in this case, the direct linear relation between the explicative and predictive variables is not imposed because we consider these two terms. The term when we consider the distribution of the histogram and the term when we consider the distribution, when we consider the representation of the symmetric histogram. So in this case, we have a direct relation between the explicative and predictive variables if the value of A is greater than the value of B. And we have inverse relation if the value of B is greater than the value of A. So now about the discriminant, about the symbolic discriminant analysis. Considering the concept of linear combination, Diaz, Brito, and Amaral proposed a discriminant function for histograms. In this case, the score for each unity is obtained considering the definition of linear combination previously presented. Comparing the discriminant function in classical statistics and in symbolical case, we observe a similar behavior. So the score is defined using the concept of linear combination that in symbolic case consider two terms for each variable and non-negative constraints are imposed to the parameters. In classical case, if you consider the weight vector gamma and the matrix T, the matrix of the sums of squares and cross product, this product is equal to the sum to the square of the distance between the score and the mean of the scores. Similar in case of in symbolical case, if we consider the weighted vector and the matrix of the sums of squares and cross products, in this case it is possible to obtain also the square of the distance between the scores, the quantile function of the score, and the barycentric score. In classical model, the matrix T may be decomposed as a sum of the matrix B of the sum of the squares between groups, and matrix W, the matrix of the sum of the squares within groups. In case of symbolical situation, according as the Yuying theorem is verified, it is also possible to obtain a similar decomposition in case of symbolical and in classical case. Because of this decomposition, the parameters of the model are estimated such that the ratio of the variability between groups and the variability within groups is maximized. However, in symbolic situation, we have a constrained fractional quadratic problem, and because of this, we have a hard optimization problem, a no convex problem, easy to find a good solution, but difficult to prove the optimality.
Sonia, in the interest of time, please just about 4-5 minutes, if possible.
Okay.
Thanks.
Using to solve this optimization problem, the Baron technique and the conic optimization is used. So consider the malus distance and the discriminant function. It is possible to classify one observation in one of two groups. In this case, it is possible to calculate the score of the observation and the barycentric score of the group 1 and barycentric score of the group 2. If the malus distance between these two quantile functions is lower than this value, the observation is assigned to group 1, and if this value is lower than this, in this case the observation is assigned to group 2. So, in conclusion, if you consider the study that we present in first part of this presentation, when the goal is classified bacteria in gram-positive or gram-negative, in this study we have 11 bacteria in gram-positive and 12 bacteria in group that when the variables are gram-negative. To define the discriminant function, we consider the 23 species, and consider these species, it is possible to obtain the parameters of the discriminant function. In this case, you consider the leave-one-out cross-validation, and the values of the parameters are obtained considering the Baron optimization method. Here you may observe the results. The better result is obtained in case 1. In this case, when we use the leave-one-out, the values of the percentage of well-classified observations is 78%, but when we don't consider the leave-one-out, this value increased to 18.3%. In case 2, the better results are obtained when we consider the nucleotides in position 1. In this case, the values are very similar in these two cases. So some conclusion remarks, but as I have too many time, some future work. The future work is to develop the method to allow for the classification in more than 2 groups and apply the linear regression and discriminant methods to other real situations. Thank you very much for your attention.
Thanks. Thanks a lot. Great presentation. Excellent. So if there is not no question, Paula will surely have a lot of discussion following this. I suggest we move further to the final 4th presenter, Boris Beranger, again on distributional data. Thanks again, Sonia. Great.
Hi, everyone. Can you hear me well and see the slides?
Yes.
Yeah, okay. Thank you, Andre. So the talk that I will present today is a mix of some works that I've done with Juan Lin, Scott Sisson, and Tom Whitaker. And to dive straight in, if you look at the YoungStatS blog post about today's event, I found the following definition about SDA. So with the development of digital systems, very large data sets become routine. However, standard statistical approaches do not have the power or flexibility to analyze these efficiently and extract the required knowledge. So this resonated quite deeply for me because that's the way I see symbolic data. So I see and use symbolic data as a mean to analyze big data. So a big data set that is going to be large and complex and potentially too large to analyze or too large to store on your computer. And so what you want to do is summarize this big data into a smaller data set that is going to be made of symbols. So by aggregating your big data into a smaller data set, you have some statistical questions that come to mind. The first one is, how do you summarize a complex and large data set? So you want to do this in a way that you're going to retain most of the information and the relevant information. And also, how do you do a statistical analysis on this symbolic data? So all this is going to be very useful when you have data storage problems or questions, when you have problems of computational efficiency, so it's taking too much time for your statistical analysis to be performed, or data privatization, or simply when you have non-standard form of data due to some measurement process. So what I want to present here is a possible approach that we've considered with Juan Lin and Scott Sisson. And in this one, we have defined the symbolic random variable S to be the result of an aggregation function pi that is done on x1 up to xn, my IID random variables that are the underlying ones. And by creating my symbolic random variable S in such a way, I can come up with a likelihood that is going to take as input the symbols. So my likelihood L is a function that takes as input S and is a function of theta. So what is theta here? Theta is the parameter of the model that I would like to fit at the underlying data level. So as you can see, my symbolic likelihood is going to be expressed as an integral, but in that integral, I have a L of x given theta. That's my standard likelihood that I would use if I had all the data at hand. I do not have all the data at hand. I do not have x. And so I'm going to integrate with respect to x. I have a g of s given x function, which is explaining the mapping to go from the data x to the symbolic data s. And so by doing this, we're able to fit a model at the underlying level only using some symbolic data. And if you consider that you have no generative model, so you don't have the likelihood L of X given theta, then the function g of s given x is simply g of s, and there are some parameters psi, which means that you do not have the integral to perform, and you come up with the existing approach that was given by Lohanmacher and Billard, where you're just proposing some model for your symbols directly. Just to give you an example here, so we're looking at how to construct a histogram with random counts. So my symbol S, again, is the aggregation of my x1 up to xn. And what it does is we're going to assume that we have some fixed bins, so B1 up to BB. And we are going to have our symbol to be a random vector of counts. So what we do is for each bin, we're going to count the number of points that fall in that particular bin. And we reiterate the process. So that's the aggregation function. And then the likelihood function that comes out of this is the multinomial distribution. So we can see that the likelihood function, the symbolic one, is going to be proportional to the multinomial distribution, where the probabilities PB are in fact the probability to fall in a bin, and it corresponds to the integral over the bin of the density that I have at the underlying for the underlying model. So the picture here that you have is some data that was generated, so 1,000 data points. We aggregated it into a 11-bin histogram, and we just fitted both times the GV distribution. And you can see that both the black and the dashed red lines are very similar. So it seems like the method is making sense. All this is assuming that we have IID data. If you want to look at not IID data, we have some results in a paper with Xin Zheng and Scott Sisson. So we can do some checks about this method and see if it makes sense as we think it does. So we can think that classical data is just a specific case of symbolic data where you have no internal variation. So in a case of a histogram with random counts, if you increase the number of bins to infinity, what you're going to end up with is point masses. And then at each point mass, you will have either a count of 0 or a count of 1. So 0, you have no data point. 1, you have a data point. And if you look at the limit of our symbolic likelihoods, you will see that you're going to recover the classical likelihood. So that means that we have some consistency, because if we increase the number of bins to be large enough in our histogram, we should be able to recover the same analysis, statistical analysis, that we would do on the regular data. There is a nice property in all this, is that where computation is scalable. That means that if we do not change the number of bins that we have, I can increase the number of points to whatever I want. It can go very large. The computation time is going to remain the same. There are also some other symbols that we could consider, such as histograms with random bins. So in that case, we have fixed counts, and then the bin locations are going to vary. Now I want to show you 2 examples where we used this methodology. So the first one is on meta-analysis. So often what happens in meta-analysis is that a study is going to report the minimum, the maximum, and some quartiles. So we have a vector from Q0 up to Q4. And from there, the goal is to estimate the sample mean and the sample standard deviation. So the sample mean, there was an estimator proposed by Lu et al. In 2018. And for the standard deviation, we have 2 estimators from Wang et al. And Shi et al. What we need to note is that despite being used a lot in the literature, these estimators are going to assume that the data is normally distributed, which is not always the case, right? So we're going to use our symbolic data mindset and think that the vector Q0 up to Q4, in fact, is going to represent a random bin histogram. So a histogram where we fixed the counts, but the bins are going to vary. And here in that case, we have 4 bins. So we do a quick experiment. So we're going to generate some data that is coming from the normal distribution and the log normal distribution. So a distribution that is not symmetric, to just change it up a little bit. And then we're going to compare the estimated and true sample values. We're going to take the distance between the estimated sample mean and my true sample mean. And we do the same for the standard deviations. We're going to repeat it 10,000 times. We're going to consider different values of n. And just to make things easy, we considered n was 4q plus 1, where q is a natural number. That means that k, which is our vector of order statistics, is going to be 1, q plus 1, 2q plus 1, 3q plus 1, and n. So the first result that we get here is for normally distributed data. So on the left-hand side, you have the estimate that we get for the sample mean. In light green, you have our estimator, assuming that the model that we've put is the correct model, so normal assumption. And we compare in red with the Luo et al. Model. You can barely see any difference there. So they're performing very, very similarly. And they're both doing a good job. Now, when you look on the right-hand side, what you can see is in light green, it's again our estimator. And then in purple and in blue, it's the two competing estimators from Shi et al. And Wang et al. What you can see is that their estimator needs to have a sample size that is large enough such that they have a good estimate of the standard deviation. Whereas if you use this symbolic data-based approach, you can have a small sample size and it will work for you. Now let's look at the case where the data is not normally distributed. So our method is now in dark green when we assume that we have a log normal distribution, and then it's in light green when we assume that we have a normal distribution. So that's the magic of the method, is that we can assume whatever model we want. As you can see, the Luo et al. Estimator of the sample mean in red and our estimator when we assume normal distribution are not performing well. But if you assume the correct model, the log normal, then you can do a good job. When you look on the right-hand side at the standard deviation, you see something similar. The two estimators, the blue and the purple, the first one is decreasing and then increasing, the other one is just decreasing. They are never going to give you a good estimate of the sample standard deviation. Nor is our estimator if we're going to assume normal distribution. However, if we assume not log normal distribution, then we're going to perform very well. So that means that we can be a little bit more flexible and improve the methods now currently available in the literature. In our manuscript with Randin and Scott Sisson, we touched a little bit on symbol design, looking at such problems. So you can refer to the paper if you want to know a little bit more about it. The second problem that I want to show you is a classification problem. So we have Y, that is a response variable that is going to take K possible outcomes. So I'm going to call them from 1 to K. And X is going to be some explanatory random variables. And the classification is going to be done using logistic regression. So here, if we take the example of the multinomial logistic regression, we have our likelihood that I call LM is the product from N1 to big N. So it's the number of observations that I have. And then I have the product for each of the outcomes K of the probability that Y takes that outcome K, given that we have observed the explanatory variable. And all this is to the power an indicator function that is making sure that we only take the probability for the correct outcome. And these probabilities, it's given below, they are the ratio of two terms that depend on some exponential terms. There is another logistic regression type of model, which is called the one versus rest. It works very much in the same way. I'm not writing it here because the expressions are not as nice to write, but the idea is exactly the same. So how do we do our prediction? We're going to do a predicted value for my yn to say n is going to take the outcome, sorry, yn is taking the outcome k which is the K that is going to maximize or have the largest probability. And then the prediction accuracy is just taking the basically the average of the correctly specified predictions or outcomes. So what are we going to do here in our SDA context? For each of the possible outcome, I'm going to sort and take those that have, for example, outcome K, and I'm taking all the predictors, and these predictors are going to be aggregated into a histogram. So I have a histogram, d-dimensional, for each of my K possible outcomes. But the histogram is for my explanatory variables. So in that way, we can come up with, because we are working with histograms, we can come up with the likelihood function for this kind of model. So instead of having a product from N1 to begin, we have a product that is going to go from bin K, that is going to be the first one up to the BK ones. So we're going to do the product over all the bins, and our probabilities are going to be integrated over the bin range. There are some statistical improvement that can be done here. We can do a mixture of symbolic and classical contributions. If there are some contributions that you think are very important, you can just consider them as is. And where it's not as important, you may want to aggregate into a histogram. There are some computational improvements that can be done using a composite likelihood approach. This is done so because you see that we have to do an integral with respect to x, and x is going to be the explanatory variable. It can be high dimensional, so the integral can be difficult and time consuming. And so in that case, it may be a good idea to work with some composite likelihood approaches. So I'll give you a quick example. So there's this supersymmetric benchmark data set that is available on the UCI database. That's a data set of 5 million observations. And what we have there is some binary responses. So K is equal to 2. It's either a signal process, so it means that it's a process that is going to produce some supersymmetric particles, or it is just the background process. We have 18 features. So as you can see, it's high dimensional. We will have to do the integral, which might be difficult to do. And so we're going to compare our performance, so our ability to correctly classify the outcomes. We compare to the optimal subsampling method that was provided by Wang et al. In a 2018 JASA paper. We divided the data into 4.5 million for training and then 500,000 for test data. And we did something that is relatively crude. We used a marginal composite likelihood approach. That means that we only considered marginal histograms, so a univariate histogram on each of the explanatory variables, the 18 of them. And so we have a histogram with random counts here. So as you can see, as we increase the number of bins, so from 6 to 8 up to 25, our prediction accuracy goes from 74.4 up to 78. In brackets below, you have the computation time in seconds. So it took us 13 seconds when we had 6 bins for our histograms, up to 21 seconds. It's not too bad. And in fact, if you compare to the Wang et al. Approach, the accuracy was 78.2. So we're doing pretty much as good in terms of prediction accuracy, but they took 86 seconds. So we take roughly a quarter of the time. So in a quarter of the time, we're able to provide the same prediction accuracy. One thing to note is that if you are interested in the regression coefficients, then our method is not going to be as good as the subsampling method because the subsampling method is, in the first place, looking at this, estimating these regression coefficients. So quick conclusion, I presented a new approach to SDA. So the goal here for us is slightly different compared to what other research has been done in SDA. We use SDA as a mean to estimate and fit models at the underlying classical model. So basically what we see is we take the classical data, we do not see it, we observe it latently through the symbols. So we only see the symbols, we do not see the classical data. And then we can recover some of the existing models, as I explained earlier. And it should work in principle for more general symbols. This is something that we're actually currently working on, providing more symbols that work better in higher dimensions than the histogram, because the histogram will have some issues if you want to go in very large dimensions. We are looking at the properties of the estimators that we get. So this is Prosha's work. So Prosha is our PhD student with Scott Sisson. He's working on this. We're also trying to implement this for more sophisticated statistical models. We're looking at the trade-off between accuracy and computation. So how much do I want to aggregate my data to be much faster, but how much information am I losing? So we want to try and quantify this. And then finally, we're looking, we did some preliminary work, but we'd like to spend a bit more time on the design of the symbols. So what is the best way to aggregate the data to get the best results? So that's it for me. Thank you for listening. Here I've listed 2 manuscripts in orange that are the 2 that I've talked about in this presentation. And then I mentioned the composite likelihood approach, which is the 3rd one. And then I'm just advertising Prosha's work that used SDA for some modeling internet traffic data. Thank you.
Thanks. Great. Thanks a lot. Great presentation as well. Excellent. So without further ado, I would give the floor, because I can see no questions still in the chat, to Paula Brito to comment on the 4 presentations. Professor Paula Brito, please, the floor is yours. Paula. We do not hear you, Paula. You're muted. Okay.
Okay, I trust you can now see my slides.
Yes.
Okay, so I'd like to start by warmly thanking Andres Rakar for organizing this webinar in the context of YoungStatS. Thank, of course, all the 4 speakers for their interesting and clear talks. And of course, thank all the participants for joining us today. I will try to be brief, and more than asking questions, I will perhaps just point out some issues or some points that, or make some comments that came to my mind while following your slides and hearing your talks. So is this not proceeding? Here. So to start, this webinar is concerned with advancements in symbolic data analysis. So I just recall that symbolic data has been introduced, defining new variable types able at representing units which have inherent variability that should be taken into account. And to do so, data address new forms, not only single numerical or categorical values, but data appear in the form of finite sets, intervals, or distributions. And these may be directly available as such, like in the description of biological species, or in the intraday variability of financial assets, like it was used today in illustrations, or they can arise from the aggregation of large amounts of data that can be open data, collected data, generated in some contexts, individual records. Of course, when our data moves to these non-trivial forms of set-valued, interval-valued, distributional-valued, this requires new approaches for data analysis. From a statistical point of view, the usual models and methods may not apply because usual properties may not be taken for granted. Most approaches developed so far, I would say, rely in either of two principles, which one consists in representing the symbolic observations by a set of real numbers. In the case of intervals, this could be the lower and the upper bounds, or the midpoint and the range, for instance, and then propose methods that use these values in some appropriate way. Alternatively, some authors considered symbolic observations as such. For instance, the full interval or the full distribution represented by a quantile function or a distribution function, maybe with some underlying assumptions. In today's webinar, I would classify the talks in the following way. The three first talks are concerned with analyzing data sets whose statistical units present variability. That is, the units of interest are the so-called symbolic units. These are the statistical units of interest, and they present variability. The first two addressed multivariate analysis of interval valid data, proposing methods for regression or cluster-wise regression with SOMs. And the third talk addressed multivariate analysis of distributional data, focusing on discriminant analysis. The fourth and this last presentation is somehow a bit different because it's not concerned with higher level units, but use symbolic data as a means to model the underlying, that is classical, real valid or categorical valid for discriminant analysis, statistical units. Now I will go one by one through the talks and just try to summarize the main points and raise some questions or some comments, take them more as comments than questions. So in the first talk, model averaging for interval value data by Yuying. It was presented a model averaging approach for interval valid time series data, which allowed, or with the objective to cope with model uncertainty, and therefore adopting a model averaging approach rather than a model selection approach. In this work, intervals are modeled by midpoints and log ranges, but still the author proposes a model for the ranges for which a correction is developed. The simulation study shows that the proposed approach works well, overcoming the results for benchmark methods. And then we saw an application to the prediction on crude oil pricing. Some questions that came to my mind. One first is the real valued case a special case? That is, when all ranges are null in the data, do we get a similar model or the classical model for real data as a special case? Along a bit in the same lines, does the model allow for real valid exogenous covariates? And then it's my understanding that the model relies on error measures based on squares, L2 type L measures. What about concern using L1 measures as an alternative? I mean, my point here, what about robustifying the method? Can something be thought to make the approach, the method more robust? Second, sorry, but my slides are not moving.
Maybe Paula, if you unshare and share again.
Yeah. No.
No.
Yeah, here we are.
Yes.
Here we are. Sorry. So the second talk by Bruno Pimentel presents us a method for Conan mapwise regression applied to interval data. where sum-wise regression is a method for sum-wise regression is developed for interval valued variables, where interval data are, and this is one of the questions, represented by two values for each interval. And the first question is, it was not so clear to me whether they are represented by lower and upper bounds or by centers and ranges, as in the benchmark methods, I think that were mentioned. Then in such methods, one question is there any guarantee that the predict upper bound is always higher than the predict lower bound? And if not, what would be the solution? Then any ideas on the choice of the size, and not just the size, the topology of the map? How does the performance depend on the choice of the distance? I believe it was mentioned that the Euclidean distance was used. Have you tried with different distances? How does this work? And again, the loss function is a L2 function. Is there a possibility of extending or developing a version of such method with a L1 loss function? Again, in the interest of robustness. Let's see, yeah. Third talk by Sónia Dias. Now we move from interval value data to distributional data in the form of histograms, for which linear discriminant analysis method is proposed. This relies on linear combinations of quantile functions where two terms are used for each variable. Then the coefficients of the linear discriminant function are obtained by maximizing a ratio. But in this case, given there is a non-negativity constraint on the coefficients, this is now, as opposed to the classical context, a difficult optimization problem, which requires special approaches. And then there is the rule for classification into a priori groups, which is a distance-based rule. Now, comments or issues would be how can we extend this method for more than two groups? Do the results depend on how the histogram is defined, is on the number or the position of the classes, these of the bins of the histograms? And given that we need two terms for each descriptive variable, I foresee some limitations when the number of observations of units is not so large, because this raises some estimation problems. And finally, in the last talk, Boris Beranger discussed how to use symbolic data to understand the underlying data behavior. That is, as opposed to the other authors, the aim is now to analyze or to model the classical data, the underlying classical data, but relying only on the aggregated information. So this is based on defining symbolic likelihood, but for the parameters of the classical model, of the model for the underlying data. The method is shown to be consistent and computationally scalable. Histograms have been considered either with random bins or with random counts. That is, when we fix the frequency or and then the bins are random, or we fix the bins and then the counts are random. And also question is, what of these two approaches would be more appropriate? To the results depend on this. Then we saw applications to both meta-learning and classification. So already I started with this question, do the results depend on the form of the aggregation? It can aggregate in the form of intervals, that is histograms with just one bin, histograms with more or less bins, random bins or random count. How does this play? During your talk, I heard at some point that we're using multivariate histograms. It's not clear whether we are using multivariate histograms, the joint histograms, or as it is usual in STA, the marginal histograms for descriptive variables. And then it was mentioned that the authors have proposals for symbol design. I am a bit curious about this and what would be the considered criteria. Thank you very much to all again. And as Andre already mentioned, I'd like to draw your attention to the conference of the International Federation of Classification Societies that we are holding in Porto next July. We hope to welcome you all here. Thank you very much.
Thanks a lot, Paula, for this very clear and great discussion. Probably the speakers would like to respond. Maybe we start in the order of presentations. Yuying, do you have? Thanks.
Yeah, thank you. Yeah.
Thanks.
Hi, Professor Brito. Thank you for your questions. Yeah, for your first question, you asked that is a real valued case as a special case. I think it works. If it is a classical data, like midpoint data only, without the range, so we can consider our model is for the midpoint, and we can use the Mallows type criterion to select the weighting for midpoints only. And if this this data is the range data only, without the midpoint, we can use the proposed criterion used in our paper to do model averaging for the range only. So I think the real valued case, our method works for the real valued case. Yeah, and for your second question, you asked that does the model allow for real valued exogenous covariates? I think if VR model, because in our data journey process, we use a VR model. If this real valued covariates can be added into our VR model in our data journey process, I think our method works. And you mean for your third question, you ask about robust approach. For example, moving from L2 loss to L1 loss. Yeah, in our new work, I have a new work joined with, it is also a joint work with Professor Dan Slin in Porto University. We are discussing about this idea. Yeah, we consider more general loss model averaging. So we want to do interval data for more general loss for model averaging. So this loss function can be relaxed to more general, like L1 loss or Linux loss or other loss. It is a different theory, but I think this work maybe may cover more applications in economics and finance. Thank you.
Thank you very much.
Thank you.
Thank you.
Thanks. Maybe Bruno. So.
Thank you for the questions. I think the first question is about the representation of the data. So use, yes, there is a point in the presentation, put a center A range, but use the lower and upper bound interval representation. About the guarantee to the lower is lower bound is lower than the upper bound. Use the combination of the SOM map and the parameterized method for interval data proposed by the Leandro and Souza, Renata Souza, where there is a this guarantee. They prove that the predicted interval guarantees that this happens. So they use the box cut method for interval, where the prediction is is always the lower bound is less than the upper bound. I think you also asked about the size of data set. Is it? I forgot
the size of the data set, but if there are any ideas how to choose the size and the topology of the map.
The size, yeah, use for synthetic data sets 150 points. For real data sets, almost 5,000 points. But for larger data sets, you have to try some bigger data sets.
Sorry, this was not the question. Is the size of the map the K?
Okay, so yes, if you see the literature of some coherent map, you use it's normal to find 100 nodes, but it is working. You start to use simpler maps, so lower number of nodes, and you achieve better results for simpler topologies. So from 6 nodes, you change to 12, 15, you have better results. Important point about this method that you create the topology where the nodes are fully connected, so it spends more time to converge. So if you use more nodes, for example, 100 nodes, to spend much time to. So this is a negative point about the method, but for simpler topology, we can find better results.
Okay. Listen. Maybe we go forward, or do you have anything further? Maybe we continue with Sonia. Sonia Diaz, you can respond as well. Thanks. You're muted, Sonia. Sonia, you're muted. Great.
Thank you, Paula, about the questions. For the first question, I think the extension of the method to allow the classification in more than 2 groups is a work in development. The idea in this case is to divide multiple-class classification data sets into binary classification problems. And in this case, the main techniques are the 1 versus all or 1 versus 1. The other question is about the number of classes that we consider in the histogram. In my opinion, I think the number of the classes will affect the results, but we don't study this problem. In paper that when we proposed the discriminant method, we compare the results when we consider histogram valid variables or interval valid variables, and in this case the results is best in case of the interval valid variables, because we have because in this case the number of the parameters to estimate is it's lower. In the last questions, I think it's important, this question, because in this case the number of parameters to estimate in model is 2 times the number of variables, and because of this it's not possible. We consider a big number of the variables. A lower number of variables. I think is important to study this situation in future work. And
great, maybe Boris as well.
Thank you, Andre. Thanks, Paula, for the great questions. So your first question was about the impact of the aggregation, and the granularity. So if you're using a histogram, the number of bins that you have, or their location, or if you're using intervals. So yes, so clearly, depending on what aggregation you will do of your data set, the original one, the aggregation has an impact on the estimates that you're going to provide. That's why I was saying at the beginning of the presentation, what is important is that we find a way, and we don't have it yet, to find almost an optimal way of aggregating the data such that we retain all the important information. So if we are comparing at the moment histograms with random counts or histogram with random bins, they can have very similar results if you have a large number of bins. But if you go to a lower number of bins, there's potentially more discrepancy that you're going to see there. So that's why we're looking into finding the properties of the estimators that we get, because we hope that by finding the exact properties, so there's going to be the bias and etc., and asymptotic properties, that we are going to be able to understand how to kind of select a good aggregation function. Then your second point was about whether we're using joint histograms or marginal histograms. So the way we define it is as joint histograms. So think that you have a data set that is bivariate, just to make it simple, then you're going to aggregate it into a bivariate histogram. But there are some problems, and we looked at spatial extremes problem, trying to fit max-table models, or the example of the logistic regression, where the integral that you have to do over the bins of your histograms, so you're integrating basically the model of interest over the bins. If you have too many or too high dimensions, it's going to be quite difficult to do. And so we try to do these composite likelihood-based approaches. So rather than if you had, let's say, three-dimensional, you could look at pairwise, so bivariate histograms. You can even collapse in the example that I provided for the logistic regression to marginal histograms. So the best would be to take the joint histograms, but if you can't, you can try and reduce it. So reduce the dimensionality issue that you have there. And then your last comment was about symbol design. So we don't have a proposal per se. We've done some simulations and looked into it, in particular for interval data. So when you have interval data, you could say, okay, I need to take a lower bound and an upper bound. Should I take the minimum and the maximum? Should I take this 25th quantile and the 75th quantile? Or should I take them close to the median? So it doesn't seem to be the smartest choice to go min-max. And in fact, when we did some simulations, we realized that we were looking at, we were calculating the mean square error, and we were just making the histograms, just to make it easy, they were symmetric, and we were just making them collapse in that way. And you could see that at first, we were able to decrease. So if you are taking the min-max, you will have a high mean square error, and then your mean square error is going to decrease. But at some point, your bounds are going to be so close to the median that you're going to lose too much information again. So that's where we are thinking that there are some ways, and I guess there's not a unique way to define how optimal your choice can be, but you can do it, for example, by looking at the mean square error in this case. And we say, okay, it doesn't make sense to go min max, and it doesn't make sense to go too close to the median either. So that's some initial steps. I guess there's plenty more to do in the future about these things. So thanks for your questions.
Thank you to you all for clarifying and discussing all these points. Andre?
Thanks as well. I can see also a question in the chat to stimulate, hopefully now also the debate from Professor Bidet to Sónia. What are the results of your method on your data?
This has been presented, I believe.
Yes, we can put the slides now. I think it's...
You can, sure.
You can see my slides?
Yes.
Yeah. In this slide, we have the conclusions when we apply the method proposed to this situation. This is the results. In this case, the case number 1 is when we consider as variable the distributions of the 4 nucleotides frequencies in each gene, and this is the best situation. In this case, we have the percentage of well-classified observations in 83% when the leave one out method is not considered, and with the leave one out, the percentage of well-classified observations is 78%. When you consider the second case, when the distributions, when the variables are distributions of the 4 nucleotide frequencies at the first, second, or third codon position, in this case, the best results are observed when we consider the first position. And in this case, the results is similar in case 2 and case 1. It's okay? It's clear?
I suggest for everybody that you now just unmute. If you have any question, please feel free to ask or put it also in the chat, actually. If there is anything additional, I think there was a lot of material for a lot of questions, to be quite sincere. Maybe I will add one small, and maybe the others come later. It is for Boris. Basically, you show this, I would say, something of a consistency result when you, in the limit of the number of the pins, the likelihood becomes a normal likelihood. Does this, do you assume this would hold for any distribution, or in general sense, or in what senses would this not hold? I think this was for Gaussian cases, right?
No, it was not specific to the normal distribution. That would work for any distribution, would be fine. Any model is going to be fine. Okay. Because if you think your histogram, just think of a one-dimensional histogram. If you increase the number of bins, your bin width are going to become smaller and smaller. And then in each bin, you at some point you end up with either a count of 0 or count of 1. And then at some point, the bin width is just going to collapse to a point mass. So you're going to end up with point masses at each of your data points, which is going to be your regular likelihood function. And it does not matter. It doesn't matter which is your underlying model. And it makes, I guess, sense because we are reducing the amount of variability that there is to the point where there's no more internal variability in the symbol.
Have you maybe considered also other forms of, like, say, empirical likelihood or similar, possibly non-parametric, or other approaches to constructing the composite likelihood perspective that you have?
That's a good question. So the answer is yes. We have a paper that is, I was going to say ready, it's a paper in progress where we have already done most of the results, and we actually look at non-parametric versions of it. So we can do some things as well in the non-parametric settings. I'm hoping I'll be able to share this with you very soon. Soon being a vague a vague time frame.
Nice. And we have an additional question in the chat, came from Edwin Diday. For Boris, how do you choose the intervals of the histograms? What about the Fisher optimal clustering approach to build the histograms?
So at the moment, we are doing very basic things where we just compute histograms. We say, okay, we want a certain number of bins. If it's a random count, we're just going to make them of equal width. So I can't remember exactly the algorithm to do it, but it's a little bit further than the min max of the observed range. And then it's just divided into equal width. So there is nothing that has been done in a smart way, I would say. It might be interesting to do that in the context of random bins and fixed counts, maybe. But it's not something that we have investigated. So that's a good question, Edwin. Probably something that we should look into, I guess. Maybe that works in high dimensions as well, which could be useful.
Anything further? I have one additional small question also for Sonia. Have you also considered possibility to transfer your approach in the two components histogram regression setting, because this is the two quantile version of your regression in Pino Verde setting? This make any sense at all?
So in the definition of linear combination, we consider two terms because it is not possible we obtain the symmetric of the histogram multiply the quantile function by -1. So in this case, we consider as a base, and in this case, if we have a direct relation between the explicative and predictive variables, the parameter associated to the histogram, to the quantile function that represent the histogram value variables is greater than the value of the parameter associated to the symmetric histogram. And if the value of B is greater than the value of A, in this case, the relation of the explicative variables and of the explicative variable and the predictive variable is inverse. So this is the solution that we consider to solve the problem of the semi-linearity of the space when the elements are quantile functions.
Okay, thanks. Another question from Edwin Diday for your results, Sonia. What is the link to nucleotides in the chat?
What is the link?
I could say that the paper with that application is not yet out there.
I don't know what to answer in this case.
Great.
I don't have another results about this application.
Yes, but at the beginning you have shown
this is
the nucleotide and the percentage and so on, and as a result we don't see what how this intervene, how this play. You have presented the nucleotide at the beginning, A, B, C, D, but you didn't show in your results how this percentage
in this case the results is not bad. It's good, but in future the goal is consider more species and analyze this situation, consider a big number of species, and in this case verify if the method classify or allows a good classify the bacteria as gram positive or gram negative.
Okay.
Thanks. Any other question? You have some congratulations. The chat to all the speakers. But if there is any further question, the audience or from the speakers.
Andre, I was just thinking of Edwin's question about the Fisher optimal clustering method. So maybe I can maybe think of provide a maybe more in-depth answer, if that's okay. I think so. If we use that technique to build the histogram, you're probably able to come up with a histogram that is going to reflect well the data that is in this histogram. But I guess the question is this going to be the most helpful for the model that we want to fit? Because the histogram is just what we observe and it is what it is. And then there is the model that we want to fit. So I think that's a good approach to look at. It would be definitely interesting to see if we use that clustering approach, if it's going to give better results than, you know, for example, just putting the bins, just equal bins. So I think it's something that can be investigated.
Yes,
and probably
yes, you're
worth.
right. But if you do this kind of clustering method, the intervals will not be equal. You will have intervals of different size, but in that case, you have just to divide by the size of the interval, and so you get the pattern of the good histogram. So yep. I think it can be interesting because you fit better the data with the histogram in that case. I suppose that I'm not sure, but I think you have clusters inside the intervals.
Yeah, that makes sense. So there's probably a good chance that you would get a better estimate of the model parameters. That's something that can be done in simulations, I guess, and we can quantify this. So how much better do you do with that technique? Because at the moment we really, you know, try things in a sense where we say, okay, let's assume that we have that many bins, and then we put them where we think it's a good place, but it's not random, but it's not also, you know, clearly defined. So maybe having a good mechanism would be great.
Great. If there is no further question, then I just thank to all the speakers, to Paula for the great discussion, to all the participants for your questions and attending. The webinar was recorded and it will be put on our YouTube channel, so this will be accessible to all. Thank you again. The next webinar will be in 1 week already from YoungStatS on algebraic statistics, on algebraic approaches to maximum likelihood estimation. Hoping to see you also there or on any further webinars. So again, great thanks to all, and to see you soon on any similar event, in particular naturally in symbolic data analysis. Thanks to all. Thank you.
Thank you to all. Thank you, Andre.
Bye.
Speakers, all participants. Thank you very much.
Bye.
Bye.